A very good afternoon, Honorable Dr. Dinesh Kabra sir, dear participants. Today we have a very, sir, your screen is visible, sir.
Perfect.
Okay, sir. Today we have a very renowned personality, a Cambridge fellow, Dr. Dinesh Kabra sir, and who is going to talk on emerging photonic materials and their applications in optoelectronic devices. Dr. Dinesh Kabra sir, presently professor at the Department of Physics, IIT Bombay. He is associated faculty member at Center for Excellence in Nanoelectronics and National Center for Photovoltaic Research and Education, IIT Bombay. Before joining IIT Bombay, he was Herschel Smith Research Fellow for Project on Energy Sustainability at Cavendish Laboratory, University of Cambridge, UK. He is also honorary postdoctoral fellow of Trinity Hall College, Cambridge, University of Cambridge. He did his PhD from Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore in 2007. He has published more than 100 research papers in international journals. He has 12 international national patents in the area of active matrix display, flexible photovoltaic panels, and nano generators. We can say that he's a patent man with 12 patents to its credit at this early age. He is a recipient of Early Research Achiever Award 2015 and Best Paper Award 2016 of IIT Bombay. His current research interest involves solution processable inorganic and organic semiconductors to understand their charge transport and photophysics and transfer that knowledge to design high performance optoelectronic and piezoelectronic devices. We are very much fortunate to have a renowned personality, Dr. Dinesh Kabra sir, who has worked at Cambridge University, and I welcome on the behalf of myself, on the behalf of my institute, Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur, Maharashtra, and on the behalf of participants, I request Dinesh sir to please proceed with his presentation and talk. Please, sir. Thank you, sir.
Thank you very much, Dr. Vijay. It's my great pleasure to be here and present some of the work which we have been doing in the last few years at IIT Bombay. Today's talk will be focused on some of those emerging photonic materials which have made huge impact in solar cell technology. So I would like to acknowledge NCPRE in the center of the photovoltaic research and education, where I have my laboratory, and IIT Bombay, of course. If you have any kind of questions related to this presentation, I'll be more than happy to receive email on the email ID which is mentioned on the first slide of my presentation. You can make a note of it. If you are shy not to ask the questions during this presentation, I welcome your questions offline over the email. Either me or one of my research scholars will respond to you. So in the recent days, as Dr. Abhijit mentioned, that I work on the organic semiconductors and inorganic semiconductors. So this is like hybrid organic inorganic perovskite absorber. So these are the chemical structure of these systems. These semiconductors are becoming very popular in current days because of their tremendous progress in photovoltaic research. These are the polymer systems which has got this lead atom sitting in the centers, and there are this purple halide ion sitting on the corners. So this is PBX6 octahedra, and in between these two octahedras there is an organic cation. This is CH3NH3. So there is a light blue color carbon and then black color ammonia is there, and the CH3NH3 ion is sitting between the this PBX6 octahedra. All these things, this is a kind of ionic semiconductor. So you talk about the ionic radius of the ABX3 formula. You have CH3NH3 as A, B as a lead or metal, and X is iodine, bromine, or chlorine. So you have this ABX3 formula of the perovskite, in which you can determine the tolerance factor T by knowing the ionic radius of the respective constituents, and that allows you to determine what is the value of T. If the T is 1, that it gives a perfect cubic structure. If the T is between 0.8 to 1, then it gives tetragonal. If T is less than 0.8, then it becomes orthorhombic. And if the T is more than 1, then these are the like kind of 2D perovskite sheet kind of semiconductors. Usually the most popular halide perovskite, these are halide and the perovskite structures. So they are also called as halide perovskites. So most popular halide perovskite is CH3 NH3 PbI3, or it's called methyl ammonium lead iodide, or MAPI. So these are the various name of the same chemical structure, and that is being used as an absorber at the early days. And the efficiency of these solar cells started with 3.5 few years back, and within like few years the efficiency have made a huge progress, unprecedented progress in the photovoltaics community, reaching from 3% to close to 25.5 is the latest number. It's a truly remarkable. However, there's a lead sitting here which is known to be toxic. So people thought many Western world countries don't allow this kind of panels to be installed on their roof, and because of the toxicity of the systems. And as I was telling, these are basically ionic semiconductors. So you basically use to ionic salt, like what our salt formula is sodium chloride, NaCl. Instead of NaCl, you have lead iodide, lead chloride, lead bromide, and you have organic salt, methyl ammonium iodide, methyl ammonium bromide, methyl ammonium chloride. So you mix the two salt together, and you go and have your cup of tea, and you come back to your office or your lab, and you find the two salt which were white in color have changed their color to blue or black. And why? Because now those salts are not anymore lead iodide or methyl ammonium iodide. They have become methyl ammonium lead iodide. So they do reactions with little bit of moisture around, and humidity is always there. So this is the way these perovskites are formed. They are spontaneously formed. You really do not need to do very hardcore synthesis or hardcore fabrication, molecular beam epitaxy or vacuum processing. It just happens spontaneously, and that's why this is like a kind of research which is possible even in small colleges. I'm stressing on this thing because I'm understanding my audience are of with the less resources. So I'm basically trying to motivate you people that if you want to do something of this sort of thing, if you have a little bit of equipments around your college, then you can really work out on these kind of systems. These materials are also not very expensive because these are salt, like sodium chloride, 7 rupees kg, correct? So 7, 8 rupees, 18 rupees में Tata salt का पैकेट आ जाता है. उसी तरह से lead iodide, lead bromide, lead chloride, they are also not very expensive as compared to what we used to buy this dye-sensitized solar cells or organic solar cells. The materials are very expensive, but perovskite materials are relatively cheap, and they are crystalline in family. Because of that, we are talking cubic structure, tetragonal structure, orthorhombic structures. So that also allows us to have a better understanding for our students. If the students wants to understand how does the crystal structure affects the charge transport property or photophysics property, they will be able to appreciate that part. So the lead toxicity and the tin state. So people have basically, since they realize the lead is toxic, so we should not be having the lead. Can we have the replacement of the lead instead of the B positions? Can we have something different? So that was the idea. So this laser pointer is visible, I believe. So this B atom is being replaced from lead to tin, but the tin is certainly not toxic, but the tin has got 2 oxidation states, +2 and +4, and that is a major concern. Most of the people have failed to make this thing, but recently, just few months back, before the lockdown, there was very recent progress happened in the making the stable tin-based perovskite solar cell, which I'll be discussing in today's talk. So what are these halide perovskites? So this is like cubic structures, and it's orthorhombic, tetragonal. So these are just the shape, and these are the various kind of ABX3 perovskite which I was talking. You see that iodine, bromine, and Also at the B side, you have the tin, you have the lead, you have tin, and on the A side, you have Ma, Fa. These are all like halide hybrid perovskite. So Fa is formidinium ion. Instead of methylammonium ion, you are using Fa ion. And at the same time, on the A side, if you want, we can use inorganic cation as well, like cesium. So depending on those all radius of these ions, we will be putting them into that various zone of this tolerance factor, and that will decide the crystal structure. That is what is being shown with the different color scheme. That in this you have got orthorhombic, there you have cubic, and there you have tetragonal. So that you can identify by knowing this radius of the various ions. Nowadays the world is all about artificial intelligence and machine learning, and the periodic table has got more than hundreds elements. And as I was telling, that we have ABX3 formalism, so you can have the various kind of these all ions, because we know the atomic numbers of these ions, atomic number of these atoms, and you know the radius, and you can find out if you remove the 1 or 2 electron from that one, then what will be the next radius by simply your first year knowledge. And you have also B side, instead of lead, you can have the gallium, you have germanium, you have tin, and on the X side, you have all the iodine, bromine, chlorine is there. But at the same time, you can use some of the rare earth metal as well. There is a people have done with the beryllium, magnesium, so these alkaline earth metals. So based on all these different combinations, you can make hundreds of halide perovskites, and those all are having the tolerance factor within the limit that they always form the 3D perovskite. This is for the 3D perovskites, you can have all these kind of combinations, permutations, and that is what is basically referred in this particular publication from, I think, Berkeley, University of Berkeley, USA. So the beauty about this perovskite is, so here I'm showing that GIF image of the perovskite. You see nice balloons of this octahedra PBX6, and in between those voids, there are the methylammonium ion is sitting, and this methylammonium ion has got lots of extra room to wiggle around, to move around, and that basically being it electronically active. Once the you shine the light, which has got always light is what? Light has got electric field and magnetic field. It's all pointing vectors. So that electric field will basically align these ions in that open space of the octahedra. And once that methylammonium ion gets aligned with respect to incoming light, so that distorts a bit of this octahedra, and that distortion basically introduce the additional kind of phonon related things, and lots of interesting photophysics takes place. So while keeping the crystallinity intact, but changing the crystal structures in the presence of light and all, that becomes very interesting. Moreover, when I talk, these materials are being used as being used in solar cells, that immediately tells the band gaps are in the range of like 1 to 2 electron volts, and that kind of band gap material uh, with crystalline nature and solution processable. So the crystallinity and solution processability, both of them are rare things. You can make zinc oxide film also by the solution process, but if you make the zinc oxide by the sputtering, you get much better crystalline property. But these perovskites, as I was telling to start my talk, that you have the organic salt, you have inorganic salt, you put them in the same paper, and you go for a tea, and you come back and you already form the perovskite. That will not happen with the oxide perovskite, zinc oxide, titanium dioxide, or any kind of AbO3, barium titanate, lithium niobate kind of AbO3 family perovskite. But this happens in this halide perovskite. The formation energy is very low, and so you can get solution processable, highly crystalline film, very shiny, very nice film, and that shows fantastic solar cell performances, a kind of unprecedented success rate, and perfect optoelectronic materials on the day device was prepared. This is like I'm putting lots of exclamation mark. Why? Because as I was telling, the formation energy is very low. So the breaking energy is also low. The things which can be made easily can be break also easily. So the moment this kind of solar cells will be put outside in the real field condition and the temperature goes 60-70 degrees Celsius in Rajasthan or in Kutch or some of those Andhra Pradesh region, so these solar cells will again fall apart and you will be having your inorganic salt separately and organic salt already evaporated somewhere, gone somewhere. So these kind of challenges are there with MAPI, with methyl ammonium lead iodide. But if you change it methyl ammonium lead iodide with some other formidinium iodide, you increase your thermal stability. That goes up to 120 degrees Celsius, which will never happen on this planet. Before that, we will evaporate. We are also organic body. So right now, the temperature which goes in the range of like 45 or below 50 degrees Celsius around the globe on some pockets of the planet, and the field like temperature goes high. And when the solar cells are operating, when the JSC current is flowing at this level, so we always try to bias the solar cell at the maximum power point. We have the voltage maximum here, we have the current maximum here, but we are interested in power. We are not interested in just current. We are not interested in just voltage, because the power will be current into voltage, and this will be zero here, this will be zero here. So you find out where this gets maxima. So when you basically plot the first derivative of this curve, then you find this is the point where you can have the maximum power generated by the solar cell. So in order to get the bias your solar cell, you basically set the load according to this Vm and Im value. And when you have your solar cell biased here, that time your solar cell is having the current flow in the range of Im or Jm. At that current density, the solar cell is basically getting heat up, and the temperature can go easily in the range of 65 to 70 degrees Celsius under one sun condition. And at that temperature, if you are putting your device continuously for few hours, then if your material is not stable, if material is inherently unstable with temperature, then your solar cell will degrade very rapidly. Hence you need to ensure that your semiconducting material which you are selecting has got its own pristine, its own inherent stability first. Thermal stability is one of the major concerns. First, you need to check whether you can form a crystalline structure or not by tolerance factor. Second, you check thermal stability is there or not. If I heat up close to 60 to 70 degrees Celsius for a few hours, whether the my semiconducting material remains intact or not. If it doesn't remain intact, no need to work with that kind of semiconductor system for solar cell applications. But as an explorer, we basically learn from the failures. We know that, okay, this material has got all the good properties, but thermally is not stable. How do I make it thermally stable? Then people learned we have to change Ma with Fa, formidinium ion, and that became very interesting. And for the time being, people who were involved in dye-sensitive solar cells, who were involved in quantum dot solar cells, who were involved in organic solar cells, all of them are looking towards perovskite solar cell research, as well as the people who were in inorganic semiconductor like silicon and gallium arsenic. Guys, they also realized the potential of the semiconducting materials in terms of the efficiency as well as rapidly improving the stability part as well. So there's a huge interest from the academia as well from the industrial research within PV applications and beyond PV application. I will show you some of the examples where these halide perovskites are being used beyond PV, because when I talk about the photonics, that is there is another many devices are there, lasers, detectors, optical sensors, light emitting diodes. So those all kind of other applications, optoelectronic applications are also being explored, not only in academia, but at the industry level because of the very rapid progress, not only in PV, even in other fronts. So what is so special? We am talking with the physics department students and physics department faculty, and we have got halide perovskite, which was uh, as a new semiconducting material system, which is being explored for the optoelectronic devices. The semiconductor system was already there. Perovskites are known to us, but we were not knowing that they can work so good for the optoelectronic applications. So this perovskite, what is the beauty about this perovskite? The inorganic sublattice. So this is, if you look at this thing, when I said that this is a crystalline semiconductors, If a crystalline semiconductor means it will have its own lattice structure, and lattice structure means you have lattice parameter A, B, C. With respect to cubic, all of them are same. With respect to tetragonal, you have A and B, which are same, but the C is different. With respect to orthorhombic, you have all the three different A, B, C. So we will see those kind of some experiment results as well. But if you look at the industry of seeing in them the cube or tetragonal or the orthorhombic form, if you see in the way it's basically shown here, so you are finding that you can separate out the blue component, methylammonium ion separately and the octahedra separately. So you find that blue atom with methylammonium ion has got open space. It basically rotates around, it basically wiggle around, it can move here and there because there's enough openings are there. And perovskite PBX6, which is inorganic cage, that basically maintain the structure. So you have inorganic sublattice in disordered organic sublattice. So you have methylammonium ion has got its location fixed, but within that location, it's allowed to move around. So there's a disorder. When the things are not fixed and things are really moving, that means there's a disorder there. So you are having, and how does the structure function relationship brings new phenomena. So when I had the methylammonium iodide, methylammonium lead iodide, so lead and iodine goes in the bottom of the periodic table. If I replace my iodine with the bromine, then what will happen? The ionic radius of the bromine is smaller than the iodine. Then my octahedra, these balloons, these gray balloons will become small, and this methylammonium ion in organic cation will feel more squeezed. Further, if I remove bromine, I put chlorine, this gray balloons will become more smaller, and then I will be having my lead chloride, which will be having very small balloon as compared to iodine, and then my this organic cation, which is basically sitting in the opening space of this lead PBX6 cage, will feel further squeezed. There will be freedom of movement of this methylammonium organic cation will get much more restricted. And how does the things will change when I move from iodine to bromine to chlorine? Whether they will remain, crystal structure will remain tetragonal, cubic, orthorhombic. So this all structure function relationship changes by changing this ABX. I'm showing those what kind of A we can take. You have the methylammonium ion, you have formaldinium ion, you have cesium ion. You can in the B side, which is sitting in the center of this octahedra here. So that can be lead, that can be tin, that can be germanium, that can be gallium. On the X, which are this red atom, can be iodine, bromine, chlorine. So you can understand by changing this all size of this radius Rx, Rb, and Ra, you are going to have completely different crystal structure with different lattice constants and all, and that will bring a completely new exotic photophysics to explore. As I was telling that we do all these depositions via solution process, and furthermore, we know that each and every PBX6 is associated with one disordered organic sublattice. You have a basically inorganic sublattice in disordered organic sublattice. So that means this disordered organic sublattice is continuously moving with respect to that open space. So that basically creates lots of defects. So the halide perovskite, despite of having very good crystalline structure, is known to have lots of defects. Not really static, but most of these defects are dynamic in nature, because if you give a little bit of temperature, this vibrations will increase for the molecules. So molecule becomes much more active with respect to temperature, and then you find that this perovskite will have more defects, and you will see all those defects playing the role in temperature time dependent PL decay. However, despite of having so many defects, this works fantastic for the devices. So what goes wrong in the conceptual semiconductor physics? A semiconductor with full of defects working so nice in the devices, how is that possible? That is the question. And the answer is this is possible because this semiconductor is defect tolerant. Defects are there, but the defects do not really make any difference in the device properties, because there are the doctors sitting in the same crystal structure, same lattice, which comes and heal the defect immediately whenever there is a requirement of healing the defect. So there are because of this methyl mono ion which moves around, and even the lead iodide uh, have got very less activation energy. So lots of time you find, oh, your system has run out of the application memory to avoid problem with computer with and even you are not using. Okay, I'm getting some problem with my computer. Uh, uh, just a moment.
Okay, sir, no problem. Take your own time.
Okay, so I hope now I should be able to proceed. Yes, I'm sorry. So other thing is, as I was telling, there's a methyl ammonium ion is sitting between the octahedra case. You can imagine a charge needs to travel through this semiconductor, and there are the ions which is freely moving. So that will change electrostatic environment, and that electrostatic environment will makes the things very complicated in device perspective. So this is the thing which basically makes the things much more difficult to understand. I am just getting this issue in my laptop. It's first time I'm finding this issue. Your system is run out of application memory. Application memory. Oh God. I'm trying to, my laptop is telling that I'm running out of the memory space. So I'm trying to remove some of those applications.
Okay, sir. Okay, no problem.
Okay. So do you see the screen?
Yes, sir. Yes, sir.
Okay. So let's see that whether I hope.
Animation is also okay.
Sorry.
Animation is also okay. No problem.
Yeah. Yeah. So and at the same time, as I was telling, like there are the lattice ions are sitting, which basically should create a problem for the charge transport, but somehow we don't see those kind of problems. And I will tell why does that happen. And there's a very good large diffusion length, and that is expected because we already said these are defect tolerant semiconductors. Charge transport is somehow being maintained because if the defects are there, those defects are being healed by the some molecules which are available freely. to heal those defects. And it also shows anomalously large. Why I say anomalously? Because you have a very high PL lifetime, but quantum efficiency of these solar cell materials are very low as compared to what we see in the gallium arsenic. Gallium arsenic internal quantum efficiencies are close to 100%, 99.9%. If you have a gallium arsenic film made in the MB, so that will have the PLQI close to 100%. But these materials gives PLQI close to like 15-20%. But so low PLQI but very high PL lifetime, that is a bit anomalous character which is being observed in semiconductors. There is a theoretical findings of the large polarons. Polarons are, what are the polarons? Polarons are basically charged carriers coupled with the lattice. Ferroelasticity in centrosymmetric cubic halide perovskite, spontaneous polarizations versus soft phonon modes. So generally the ferroelasticity is observed when the crystal structure is non-centrosymmetric. In the cubic structures of the some of the halide perovskite, still we see the spontaneous charge generation. And we have done some work and that suggests that because in the cubic structure, the corner of the cubes are being occupied by the large molecular cation, methylammonium lead iodide or formidinium iodide. So since they are not a single atom, so there's a like ensemble of atoms that are like close to 9 atoms, 4 plus 4, 8 atoms, and there are much more in the methylammonium formidinium iodide. There are like NH2, 4, so 3, 6 plus 7 atoms. So these so many atoms occupying one single corner of the cube makes cube slightly tilted. And the moment the cube gets tilted, you break the centrosymmetry. And that basically gives rise to the spontaneous charge generation in this cubic perovskite structures. And at the same time, we have these phonons. Phonons are constantly basically gives rise to additional charge generations. So these are the interesting phenomena which happens due to this crystal structure and the combination of the two lattice, inorganic and organic cation. The slow hot carrier cooling and exotic phonon dynamics. So generally in the semiconductor physics, when you sign the charge carriers goes from the valence band to the conduction band. And in the conduction band, you don't really tune your light. Solar spectrum comes with all sorts of light, UV, visible, NIR, and you say that my semiconductor is silicon, 1.1 electron volt band gap. But you don't solar spectrum is not coming at just 1.1 electron. It's not just 1100 nanometer. There are the light which corresponds to 400 nanometer, 500 nanometer. That means you are shining the light much higher in energy than the conduction band minima. And what happens to that extra energy? What happens once the energy goes to the charge case goes to that higher state, hot state of the conduction band? It basically relaxes back by the releasing the energy to the phonons. It gives the energy to those moving lattice, and the lattice gets a little bit hot, and it falls down to the minimum of the conduction band, and then you basically see the emission related to the band gap of the semiconductor or photocurrent. Some of the semiconductor has got theoretical. It was not experimental. It experimentally was just observed in the semiconductor system. In this semiconductor, in order to basically relax the charge carrier within the band, intra-band relaxation requires the vibration levels to be closely associated within the thermal energy range. Then only that will basically relax back. If the vibration levels are beyond KBT range, then what happens? At room temperature, you will not be able to see your higher energy excited charge carrier will be able to relax to the next downward vibration level, and that is called slow head carrier cooling. You have hot carrier, but it's not able to cool because the gap between the two vibration levels are much more than the KBT. And this is what happens in this semiconductor of the halide perovskite, and they are ideal candidate for the hot carrier solar cells. Hot carrier solar cells allows you to get the VOC more than the band gap of the semiconductor, because you can, if you can pull out the charges at higher in energy than the band gap material, then your quasi Fermi level splitting will basically beat the easy limit, and you might get VOC which will be higher than the band gap of the semiconductor. And furthermore, right now I was talking just MA or FA, but actually, oops, why I can't go back? Okay. Oh, I didn't realize. Hello, am I audible?
Yes, sir. Yes, sir.
My presentation has been frozen.
Presentation, we are able to see hot perovskites and beyond it.
Yeah.
This is a slide.
So I was telling, like, so far I was talking about the methyl ammonium lead iodide or the formidable lead iodide based systems. However, we can have the systems with the mixture of MA and FA as well. So that will make the mixed cation, multi-cation halide perovskite, and those are the one which are ultra stable as compared to the single cation. Because I was telling, like, if you are putting your solar cell in a sun, and if your semiconductor color goes back from black to yellow, or the larger energy band gap color, then that means your solar cell material is not stable, and that can happen. Okay, I'm sorry. This is Mac. I'm not sure why. Just a minute. Let me once quit this application. I start again.
Yes, yes, sir. Sure, sir.
So meanwhile, I open. Till that time, if you have any questions from the presentation, you can ask. Okay. Hopefully, this will not have problem now. So the hot perovskite and beyond it. So the question was, like, when I was telling that we have this balloons of PBX6. So we know that this cation, this is moving. That's what I was telling. But is this the only one which is moving? That is the question. Or when this moves, because this is an ion and these are also ion, PBX6 is having ionic character. So when this moves, this must be basically making them move as well. So lots of things are basically might be changing as the light is shining on this kind of perovskite, or even at temperature not beyond T equal to 0 Kelvin, which is just theoretical. Actual temperature is always more than 0 Kelvin. At any given temperature, even if you have cooled your semiconductor, this methyl ammonium iodide or Fa ion will be rotating and liberating and rotating, and that will basically disturb this balloons octahedras, PBX6, and that will gives rise to exotic photophysics, interplay between the static and dynamic disorder. Photon recycling, facts behind it. Some of the papers published from the various groups around the globe basically use lots of terminology which was already established in gallium arsenic semiconductor. Gallium arsenic semiconductor is known to give very good photon recycling. They demonstrated that some of those experimental data which they got suggest that this perovskite also have got very good photon recycling. And but along with us, some of the Oxford group and other groups have shown okay, those data were interpreted wrongly, and these semiconductors are definitely good, but not as good as gallium arsenic. Slow relaxation, non-exponential decay time. How do we understand? And that basically whether these are the things which is observed in the gallium arsenic as well, and that basically the results which they use and say that this is photon recycling. But we can explain this relaxation, slow relaxation, with non-exponential dynamics beyond photon recycling kind of physics concept. That's what we showed, and some of other group members, some of the other research group around the globe has shown. So the high performance dynamic semiconductors, I'm using word dynamic because, as I was telling, there is something constantly moving. There is nothing static in halide perovskite. This methylammonium ion is constantly rotating in this octahedra, and that is disturbing them. So there's a molecular rotations that distorts the octahedra, and some of the times this all gives the energy, and some of those iodine ion gets released and go to the other octahedra. So there's the vacancies of the iodine ion. So these all are the like correlated motions: molecular rotation, librations in the cubo-octahedral cavity, drift and diffusion of the large electrons and hole polarons, transport of the charged ions defects. So these all are like things which takes place together and gives rise to kind of things which is not easy to understand. A lot of correlated movements. So mechanistic insight suggests that there is ion, electrons, and holes, molecular rotation, liberation. These all things are there, and that gives rise to the completely different exotic photophysics. Further, as I was telling, when I'll be changing my, you all have seen that in your daily life, you can get the different color of LEDs: red, green, blue, orange. Why? How does it happen? So generally, if I go with the inorganic semiconductor like gallium phosphide or gallium nitride or gallium arsenic, so in gallium arsenic, by adding the aluminum, you increase the band gap, and because aluminum is small in the size as compared to gallium, so your lattice constant goes down, and when the lattice constant goes down, the band gap increases. Same thing if you put the gallium, aluminum, indium, then this is the band gap range. If you have the gallium nitride, you can get the band gap in the close to violet color. But if you add indium, which is bigger in size, by replacing the gallium 1 minus X, and by adding the indium, you can get the green color emission from the gallium nitride semiconductor. So these are the recipes which were known to us from the inorganic semiconductors, whether it's gallium phosphide family, gallium arsenic family, or gallium nitride semiconductor family. So we use that kind of knowledge in our background, and we use our perovskite. This is MAPBI3. When I replace iodine with the bromine 1 minus X and bromine X, then I can tune the band gap in this range. This is pure methylammonium lead bromide. If I replace bromine with little bit of chlorine, then I can tune my band gap with this blue arrow, and you can get the pure 3 electron volts color from the methylammonium lead chloride. So you can tune the band gap all the way from UV to NIR range by a very simple chemistry. It's like you are just really adding up the different salts together, and everything happens spontaneously. This is the UV absorption data of the different semiconductors of perovskite. There is one more interesting thing which we can observe here is, as you go from iodine and you go towards the chlorine, you find your absorption spectrum bend edge. If you can see this laser cursor, so this point here, there is no additional peak, but this peak starts becoming more dominating and significant as we go from iodine to bromine to chlorine. So when you basically go towards the smaller halide ion, you find your absorption features starts dominating with one excitonic peak. This is the classical excitonic character, which is in semiconductor is seen. If semiconductor is excitonic nature, you will not get your absorption following the density of states of the 3D semiconductors formula, or density of states is directly proportional to e to the power half, and that will be making one parabola. But instead of making the parabola additional peak, and you have this e to the power half increase. So this is with respect to wavelength, This is lambda here. This is shorter wavelength. This is a higher wavelength. So, but if I plot this graph in the energy scale, then you'll be finding that this will follow the e to the power half relations beyond this exotonic peak. But exotonic peak becomes dominating as we go from iodine to bromine and further to chlorine. What happens actually? As you go from iodine to bromine to chlorine, your dielectric constant of the perovskite semiconductor goes down. And once the dielectric constant goes down, then your electron hole bound excitonic pair. What is excitonic? Basically bound electron hole pair. It's like hydrogen atom, but instead of having the nucleus or the proton, you have the hole. Hole and electrons bound together form an exciton. It's electrically neutral species, and they are bound together because they. This is what we have been taught in our 9th, 10th standard of the textbook, that positive and negative charges likes to stay each other. But and what is the binding energy between them is K Q1 Q2 divided by R, and the K is 1 by 4 pi epsilon naught. Epsilon is dielectric constant. If the dielectric constant is low, then the binding energy is high. And the dielectric constants of the MaPbCl3 is much lower than the MaPbBr3, and it's much lower for the MaPbI3. And hence they stay bound together. In the silicon, the dielectric constant is close to 12, and exciton binding energy of the silicon is close to 2 MeV, and hence when you shine the light at room temperature, which is 25 MeV, you don't generate any exciton. You directly generate free carriers, and you get the photocurrent out. So certainly from this particular graph data, it suggests that the gray portion is useful for the solar cell application. However, this very nice, very narrow actual emission spectra, these are actual emission spectra, these are not like schematic, these are all experimental data. So you see the very narrow emission is coming from this perovskite, which is clearly signature of the very good crystalline quality of these materials. And it can be tuned all the way from red, yellow, like you are making all your VIBGYOR. Your rainbow is here. So, and that is what basically the detector which we are carrying in our face, eyes, likes. Eyes are organic semiconductors. They work in the UV range only. They don't work in NIR. They don't work in the beyond UV. So we have our photopic function, which goes from 350 to 700 nanometer, and you can get all those colors by doing a very easy chemistry using mixing the lead MAX and PBX2. MAX and MAX plus PBX2 being mixed together, and you can get any kind of band gap of the semiconductor. And this is what basically we were doing with inorganic semiconductor technology. Halide Porosite band gap excitons versus free carriers. So as I was telling, we have this is MaPbI3, this is MaPbBr3, this is MaPbCl3. We could basically use 1960s Elliott theory model. Elliott is the one who basically proposed the excitons model. So we have the Frankel excitons and we have the Mott excitons. So the Frankel excitons are the molecular excitons. They are very small in size, whereas the Wiener Mott excitons are very large in size, which are available in the inorganic semiconductors, and that's what happens here as well. So we could basically separately determine the electronic band gap by separating out the excitonic contribution from the UV spectrum. So this is what is shown here, and we could demonstrate that this all happens because the dielectric constant of the system changes. It goes down as we have the more and more chlorine coming into the picture. These are the data for the MaPbCl3, MaPbBrCl. You have the CH3NH3, you have lead, and you are changing bromine and the chlorine. As you increase the chlorine concentration, your dielectric constant goes down, and dielectric constant goes down, external binding energy increases. Another interesting phenomena which we have seen is, if you see, when you basically replace the halide ion from iodine to bromine to chlorine, actually you do not make a huge significant difference in the conduction band minima, but there's a huge, very significant change in the valence band maxima. So your valence band is basically being dominated by the halide ion, whereas your conduction band is not. So by changing the halide ion in the ABX3 family, your valence band is not changing a lot, but your conduction your conduction band is not changing a lot, but your valence band is changing very significantly. Furthermore, we saw that okay, we can mix them, we can have all color tuning. So this is what you have done. You have basically red represent the MAPB I3 and the green represent the MAPB BR3. But when you shine the light on this mixed halide perovskite semiconductor and the light intensity is significantly high, then you find slowly this green starts coming together and red starts coming together. You start seeing light induced phase segregation. Light induced halide ion segregation starts taking place, and you find that they are no more emitting the single color, and they start emitting two colors of light. One corresponds to MAPB BR3 and one corresponds to MAPB I3. So the band gap tuning is which was demonstrated is all transient. It's there as long as the temperature is not high, as long as there is not enough intensity is being provided. If you are running making a solar cell with a tunable band gap pure with single MA possible. Now people have demonstrated by replacing the CH3 NH3 with Fa and mixed cation, they could make they could maintain the band gap stable without seeing the halide ion segregation. So this is what I was telling, that you have this different role of various sites in electronic properties. So this is a perovskite. You have lead p orbital which makes the conduction band minima, whereas your valence band is made using the lead s orbital and halide p orbital. If you basically replace your iodine with bromine or chlorine, then your valence band gets shifted, and hence you find that your band gap is being changed due to the change in the position of the valence band minima. Another interesting thing is your conduction band is made up of the p orbital and your valence band is made up of the s and p orbital. Whereas in most of the semiconductors, you will find holes are heavy, electrons are light. This is the very simple statement in semiconductor physics. Effective mass is a concept which basically suggests that the electrons travels more easily than the holes because holes are heavy. Why do we call holes are heavy? Because generally the valence band is made up of the p orbital and the conduction band is made up of the s orbital. So first of all, when you basically push a charge carrier from valence band to the conduction band, that means your charge carrier is in hot state. So that can move more faster. Along with hot state, you are also giving a orbital in the case of the silicon and in the case of the gallium arsenic, which is s orbital. S orbital is spherical in shape. You have got 3 degrees of freedom in all this sphere. So you have got the property of getting much more delocalized, and you have also having the hot carrier, and hence in most of the inorganic semiconductors, you will be finding electrons are having the higher mobility than the holes. However, perovskite things are different. You have got your charge carrier hot in the conduction band. However, instead of s orbital, it's a p orbital. So it basically restricts somehow electron motion. And moreover, your valence band has got s character as well. And that makes your whole mobility slightly better with respect to your electron mobility. And hence, the perovskite is the only semiconductor where you find ambipolar character. Ambipolar means you have got electrons and hole mobility are almost same for a given semiconductor, which is happening because the effective masses are same. Effective masses are same because you have got the orbital shape playing the role. orbitals which are being used to make conduction band and valence band of various semiconductors, they play the role in deciding that whether the material will be ambipolar in nature or not. And this is another very interesting observation. So gallium arsenic is the direct blue line which you see here, solid line, and you find that on the energy scale on the x-axis and the absorption coefficient on the y-axis with the log scale, you find your gallium arsenic has got very steep change. That means it's a direct band gap semiconductor and it does not have any defect related to KBT, which is the case with crystalline silicon. Crystalline silicons are also very good, but you see huge tail. If you compare now MAPBI3, you find MAPBI3 is as good as uh, gallium arsenic in terms of the energetic disorder. A semiconductor with very steep absorption at the absorption edge is a very clear-cut signature of the quality of the semiconductor, and that is directly connected to the voltage losses in the solar cell devices as well. This is another example where we could demonstrate the LED efficiencies in the perovskite solar cells. We were the first people to demonstrate in the worldwide first blue LED made up using the perovskite semiconductor. Blue is very important color. If you have the blue, you can get any color by doing the down conversion. And blue is always very challenging to get in any semiconductor. We had lots of inorganic LEDs, but it took very long time to get gallium nitride based blue LED. It just appeared in 1995. Before that, gallium arsenics and all are like very old. We had it, but making the blue color light emitting diodes is always a challenge. Even that is a ongoing challenge. We could make blue color LED, but those were not very efficient, and we are still working on some of those concepts to make more efficient blue LED. But what is there on this in this slide? So in this slide, basically, this paper was published in one of the very reputed journal, and it was editorial choice. So we made all different color of the lights, which is shown here. That is one of the ACS Photonics paper. One of the, I think this was the second paper on the perovskite LEDs in the literature, where we had the emission coming from the near IR to green color, and then further we tuned the band gap to get the blue color as well in the next ACS AMI paper, which I call it as kind of liquid gallium nitride semiconductor. And we also demonstrated that how does the efficiency of this perovskite LED is being changed with respect to the morphology of the thin films. So a qualitative correlation in the morphology to the efficiency parameter was basically described in this paper, in Advanced Functional Material 2016 paper, where we showed how much is the charge carrier balance, how is the photoluminescence yield, and how does the outcoupling efficiency, all these matter things together to decide what kind of efficiency can be achieved from the perovskite semiconductor. So that was 3D perovskite, but if you use some of the organic cation much larger than the Fa, then the perovskite structure collapses and you can make a layered structure. So this is what is shown here, n equal to 1, n equal to 2. So if you have got a basically much larger molecular cation, then you will be end up having the single sheet of the lattice, inorganic lattice, and separated by a large band gap organic lattice. So these are the very much good on the B side. And if you want to see on the energy scale, then you have the inorganic having the lower band gap and it is separated by the large band gap semiconductor. So you have sort of gallium arsenic, aluminum gallium arsenic kind of stack. So gallium arsenic low band gap, aluminum gallium arsenic large band gap. The same way you have here, you have organic layer which is having the large band gap close to 3 to 4 electron volts, even higher, And then you have perovskite, which is having the lower band gap, depending on whether you have the single layer, whether you have the double layer, whether you have a triple layer. So that will decide the change in the band gap. It's very simple concept which you might have learned in your first year of the quantum mechanics about the change in the energy level with respect to the well size. It goes 1 by L square. So the quantum well, if you have got single organic inorganic octahedra, or you have got double, if you have got triple, then the energy gap easy will reduce as the number of layer increases. If you have got 3D, then you will be saturating the band gap that will correspond to 3D semiconductor, which is here. So this is the data which is shown, like demonstrably brings new photophysics. So when people started mixing this kind of larger molecular cation, so they could see the absorption spectrum. There was this is on the energy axis. So you can see as you go towards the higher shorter wavelength side, you have dominating exotonic feature as well, and you are seeing those step kind of functions. Step kind of functions are being seen in an absorption band gap when when the material has got the 2D character. So when you have the 3D semiconductors or 3D materials, your density of states changes is e to the power half. When you have the 2D semiconductors, it goes as a kind of staircase. When you have 1D, then you have fixed energy states, and when you have the 0D, you have the delta functions. So these are the density of states versus the dimensionality is shown here. When you, instead of going from 3D to 2D, so this is the n equal to infinity, you see the spectrum, this will follow e to the power half relations. But the moment it goes beyond that, then you are seeing this staircase structure which corresponds to the 2D character. And the same thing can be seen in the photoluminescence as well. You see the energy being transferred because this is the higher energy photon that can transfer its energy to the low energy band gap material available in the same film. So when you're mixing these things, these all comes together in the single film. You have the various different band gap of the perovskite, and all the emissions gets dominated by the 3D semiconductor, because all of that energy gets funneled into the low energy emission by Foster energy transfer mechanism. So instead of basically going from iodine to bromine and bromine to chlorine to do the band gap engineering, there's another way you can do the band gap engineering. You have the same, let's say, bromine based structure, but now you can make them n equal to 1 layer, n equal to 2 layer, n equal to 3 layer, and that allows you to do again band gap tuning, and you can get the color which is like according to your choice. So these are the some of those measurements. So, excuse me. These are some of those measurements which basically allows us to do the band gap tuning by using the dimensionality as a handle. And this is that the previous one was handling with the n equal to 1, n equal to 2 layer, but here I'm talking about going from bromine to chlorine. So bromine, MAPB Br3, MAPB Cl3, both of them have got the cubic crystal structure, and hence by adding the bromine and chlorine mixing in the various compound, you see your lattice constant just follow a straight line. That was amazing result. I was very happy to see that, oh, there is no change. Lattice constant is just following a single straight line. There is no in between the change in the lattice structure. And you use the Vagard's law, and you basically fit your experimental band gap by from the UV's data with respect to the chlorine composition, and you determine your Boeing parameter, which this is basically x squared term, is 0.3. Is very low as compared to what is being seen in the case of the halide in case of the inorganic semiconductors, gallium, indium, nitride family. Because as I was telling, you can have the gallium nitride, you start mixing the indium, you can go from blue to green. The same thing, you have MAPBCl3, start making the bromine, and you can go from blue to green. And then you basically fit that data using the Vagard's law. So you have your XRD data, which can be used to plot this the lattice constant versus composition. You have your UVs data, which you can fit and determine actual electronic band gap by removing the contribution from the excitonic peak. Then you can get the electronic band gap being changed as a function of composition. So these two data are plotted here, and we could show that the uh, alloy disorder is very low in these semiconductors. You are making alloying, you are basically mixing MaPbCl3 with MaPbBr3. You have the AbCl3, AB is MaPb, and the chlorine, and then the bromine, Ab. And you are tuning this one to get how does the band gap changes, and you are looking for the B, this Boeing parameter. And the Boeing parameter, just like 0.3, is even lower than the MaPb IBr series, and it's much lower than the gallium indium nitride series. That suggests that these materials have got, they are mixing all right. They are not introducing any kind of alloy disorder, or degree of fluctuation in the crystal field is very less. The next, once you learned that we can do the band gap tuning of these perovskite semiconductors, then you might have realized in the moon mission or Mars mission, when we send the satellites, so there are the solar panels, because there is nobody will go and change the battery there. We have to basically generate the energy there itself. Fortunately, sun is shining on the moon as well, on the Mars as well, because we all are part of the solar family. So in space technologies, the solar cells are being used. Those are multi-junction solar cells. You are okay to spend more, but you want things to be much more light in the weight, because you have to send it from this planet to the different orbit. So escape velocity, you don't want very heavy stuff to be sent from here. So you want things to be light, things to be much more efficient. So you make multi-junction solar cells, and multi-junction solar cells, this is the solar spectrum in terms of energy. So you try to basically absorb each and every component of the solar spectrum by utilizing the various different kind of semiconductor, as low as germanium with a 0.67 electron volts, gallium arsenic. So this is 3 junction, triple junction. These are 4 junction solar cells. So these 4 junction solar cells are being used, and they can give the efficiency as high as 45%, close to 40 plus. And so you are basically generating a good amount of energy, and this with using these semiconductors, and that basically is the way to ensure that we can have the constant energy requirement. How do we make these 4 layers? These materials needs to be deposited using very expensive molecular beam epitaxy approach. That is the only way to make this semiconductor with all lattice matching layers and all in monolithic approach. However, we have learned in the perovskite also we can do the band gap tuning. Oxford is the group which is most famous worldwide to make very highly efficient perovskite solar cells, and that is the data. This is the paper from that Henry J. Smith's group, where they could demonstrate triple junction solar cell by solution process. They are just dripping the different color of the perovskite solutions, and they could make multi-junction solar cells using the perovskite semiconductors. And so that is the beauty, that you can make multi-junction solar cells using the solution processable semiconductor. You are not dependent on the costly deposition techniques. So we learned that we will use it for the solar cell, but how does the basic properties of the semiconductors differ from our classical textbook knowledge? Semiconductor physics is being taught by the SMG book, and these are some of the SMG book data. You see in the gallium arsenic semiconductor at room temperature, this is the way UV absorption looks like. This is with respect to energy versus absorption coefficient, and that is basically e to the power half kind of relations. If you find that you will be finding that with respect to energy, these parabolic relations come into the picture. However, the moment you start reducing the temperature, you go from room temperature to 185 Kelvin, you see your absorption spectrum starts showing an additional peak at the band edge. And this peak becomes much more sharp and dominating as the temperature goes 5 to 90 and 90 to. So that is clear that exciton binding energy, exciton cannot dissociate as the temperature goes down, and you find much more prominent excitonic feature. That is very fine. Okay, what is next observation is, if you see more, if you have good observation skills, then you find as you reduce the temperature, the steepness of this excitonic edge is also getting reduced. So you get more steep absorption than slanted absorption. Instead of having this slanted, you get much more steep. So your Urbach energy is also being reduced, and your exciton emission peak is becoming much more dominant as you reduce the temperature. If you go further down at 1.2 Kelvin, within the excitonic bands, you have lots of I'm sorry, it's not there. It's there. I'll just show you. So these are the peaks: n equal to 1, n equal to 2, n equal to 3. What are these peaks? These are Rydberg levels, which are there in the excitonic semiconductors. So these are some of the things which we always find in excitonic semiconductors. So how does the band gap? So quite a few things are there from this semiconductor physics knowledge. As you reduce the temperature, you find your band gap becomes higher. You see dominating excitonic absorption feature. Your Urbach energy goes down. And these all things are very classical, whether you talk about the germanium, silicon, or gallium arsenic. Those all data can be fitted using this Versney relation. This is an empirical relation. And most of the times, the alpha and beta values are always in this range only. Something like 0.4 MeV. So per Kelvin. So you are changing your temperature with respect to temperature. How does the band gap changes? So this is like 0.04, sorry, 0.04 MeV per Kelvin. So these are the data which basically is there for the germanium, silicon. It's not much different. All of them are in 10 from -4 range. It's just the prefactor is being slightly different. And the beta is also one of the fitting parameter, empirical parameter. But there was empirical relation. In actual sense, the semiconductor band gap changes because of the two reasons. One is electron phonon coupling, and another is lattice dilations. You know, each and everything expands or contract with respect to temperature. It just, the numbers are different. If you are basically giving heat to a plastic, it expands more, whereas a solid does not expand, but solid also expands. Glass has got its own expansion coefficient and all. So semiconducting materials also have the lattice expansion with respect to temperature, and that gives rise to lattice dilation, because expansion is what? Somehow the lattice size is changing. So we look into that aspect. So there are the two aspects, because of that the band gap changes. One of them is lattice phonon, electron phonon interaction, which is dEg by dt, and another one is lattice dilation. The first term is always in negative in energy, negative in range. So that basically reduces the band gap. As you increase the temperature, your band gap reduces. And that is what we have seen in all our classical semiconductor book knowledge and in our daily life observations. That as the temperature goes high, the band gap of the semiconductor reduces, because electron phonon interactions are highly dominating. Because our semiconductors which we are using, crystalline silicon or gallium arsenic, they really do not get affected much by the presence of the temperature. However, if your semiconductor has got lattice dilation being significantly high as compared to gallium arsenic and the crystalline silicon, you might find the results different way. And some of those kind of examples are there. In Nitride is a semiconductor, it's an ionic semiconductor, where you find things other way around. As you increase the temperature, band gap is going to increase, not going to decrease. So your temperature coefficient of the band gap is positive, not negative, which is known from your textbook knowledge. Textbook says temperature coefficient of band gaps are negative because electron phonon interaction reduces the band gap as you increase the temperature. And that is not the case with the perovskite and some of those specific inorganic semiconductor, which is this is what is being shown here. So you can see that this is a typical example of the UV-Vis absorption spectra, and this data is at 30 Kelvin, and hence you see very nice excitonic peak and a very steep absorption, and that can be fitted using this equations, Elliott's theory equation, which basically allows you to separate out the electronic band gap and excitonic contribution. In this excitonic contribution, there are lots of Rydberg levels, which are basically shown here, n equal to 1, n equal to 1 to many infinity. So these Rydberg levels are the one which basically can be seen if you do experiment at even less than like 1 Kelvin or something like that. So that is one observation. Second, as you increase the temperature 305, 225, 176, the band gap is 176 is the one which has got the lowest absorption edge. As you increase the temperature, band gap goes more towards the higher energy side. We are looking at the energy axis, not wavelength axis. So this is the data which is being shown here. In whether you have the crystallistic tetragonal or orthorhombic, you see a band gap is being more blue shifted as you increase the temperature. That suggests the temperature coefficient of band gap is positive in halide perovskites. And this is what is basically demonstrated here. And in order to explain this positive temperature coefficient data, we did an experiment where we do temperature dependent XRD. And the temperature dependent XRD allows us to determine the lattice expansion coefficient. And we realize the lattice expansion coefficient of this perovskite semiconductor is 50 times higher than the silicon. And that suggests that why we do see a positive temperature coefficient for the halide perovskite, in contradiction to the what we know from our textbook knowledge of the gallium arsenic and silicon. Further, we could explain this thing by fitting our photoluminescence data, that if you do an experiment of the PL and you fit your data at 100 Kelvin using a Gaussian distribution, it doesn't fit very well. But if you fit with the Gaussian plus exponential decay, then it fits well. Why do I need exponential decay? I know exponential decay are being used in lots of tail states fitting data. And so is that something to do with that one? We checked again by reducing the temperature from 120 to 80 to 40 Kelvin. The moment we go for the 40 Kelvin data, we find if we don't use exponential term, then also we can fit the data okay. So as the temperature increases, the defect states increases in halide perovskites because the molecular rotation vibrations are increasing in the octahedra, and that gives rise to more defects. And hence, in order to fit the PL of high temperature data, you need Gaussian plus exponential. But the moment you basically quench all those phonons, assisted absorption and emission phenomena, then you can fit your data with single Gaussian. So that was very nice way of showing the data. This paper is being highly cited, and I will say semiconductor physics students indeed should read this paper. And then in terms of devices, the perovskite versus gallium arsenic, these are the very classical review paper published from the Cambridge group where I used to work recently. And that suggests that how does the perovskite is different from the classical gallium arsenic in terms of the heterogeneity in the halide perovskite. Heterogeneity means you're thinking that you get something, but actually you're not getting that thing. There are lots of things which basically plays the role in deciding the way the perovskite will be formed. So these are on the very different length scales. You are looking at the 50 micrometer. If you further zoom it at the 2 micrometer scale, these all ripple kind of stretches looks like this. And further you make 2 micrometer to 0.1 micrometer, then you find further inside of this perovskite structure. So this is what is basically shown. I will be able to share these slides with you people. You guys will be able to see. And this is all is there in this perovskite semiconductor device structure with transparent conducting ITO, electron transporting layer tin oxide. Then you have this double cation Fa and Ma mixing PbI3, and then gold transporting layer is pyrometed and the gold contact. This is, so what kind of length scale we had it? 0.1 micrometer, that is 100 nanometer. Now this is a TEM data, high resolution TEM data, HRTM. There they, and these are the experimental data and these are simulation data in the bottom. So they basically suggest that how does the each individual atom in this particular systems are basically having an angle with the another molecules or another ions, and how does that basically changes the data at the 100 nanometer length scale, and from 100 nanometer to 2 micrometer length scales, and the 2 micrometer to 50 micrometer length scales, and then 50 micrometer to device which are in the range of millimeters to centimeters to inch. And so in order to basically understand all these things, you need to use a multimodal approach. You have to basically do X-rays. You can have some kind of pressure-induced experiment. You have lights. You have electrons, and those all kind of data basically gives rise to some kind of understanding, and that understanding can be utilized to basically further progress in the Halide Porosites. So I'll not like to continue
Dinesh
with.
sir.
Yes.
Dinesh sir.
Yes.
Immediate to this, we have a valedictory function. As far as possible, please conclude.
Yeah.
Yes, sir.
So this is again like some of the descent data on the crystal growth, which is due to the time problem I will skip because I will go to the some of the device results. So these are some of those data which is really very classical semiconductor physics which we carried out to understand the semiconductor physics of the perovskite semiconductors. But let's skip this one where I'm trying to explain why the photon recycling is not happening and something else is happening. But those are there, and those data were supported along with us from some of those Oxford group as well. So this is what I was telling, that lots of exotic phenomena happens, and these are the things which I was saying, that band gap engineering halide can be done by the halide ion exchange or by changing the dimensionality n equal to 1, n equal to 2, n equal to 3 layer. Further, we have the exotonic character, and we also have the free carrier. If you have the iodine, you have free carriers. If you have bromine, you have exotonic character. You have chlorine, you have much more exotonic character. Those exotrons can be basically fitted using the Elliott's model. We can determine the interband versus exotonic contributions by using this optical model of the exotrons. Exotron banding energies are function of the n equal to 1, n equal to 2, n equal to 3. It's function of x equal to bromine, x equal to chlorine, x equal to iodine, and those all can be connected very well with the dielectric constants which we can determine experimentally as well as theoretically. Temperature coefficient of the band gap, in huge contrast to what we have learned so far in our textbook knowledge, they are not negative temperature coefficient, but they are positive temperature coefficient, because the lattice expansion coefficients are very high, and that do not allow electron phonon interaction to dominate over the lattice dilation term. Urbach energy is very low. That suggests that these materials are really very ordered. Whatever the disorder we have seen, that comes because of the dynamic disorder, because the molecular vibrations are there in the voids of the octahedras. Heterogeneity in perovskites, as I was telling, like what happens at the 1 nanometer length scale, that drives what will happen at 100 nanometer, 2.2 microns to 2 microns to 50 microns, and at the millimeter and centimeter length scales. This part I basically skipped because I felt that I basically ask the audience if you want to ask any question. There's no point in basically overloading something which I will not be able to cover. So with this, I thank you, and I'll be more than happy to receive questions. If you don't want to ask at this platform, you can send me one email, and either me or one of my research scholar will be able to help you in understanding those things. Thank you very much. Please, uh, I'm open to have any kind of questions or comment from the audience.
Thank you, sir. Thank you for a wonderful presentation on the halide organic inorganic perovskites. Basically, it was related to the emerging photonic materials and their application in optoelectronic devices. Dear participants, the session is now open for discussion. If you have any queries, questions, you can ask immediately to sir, or if you wish, don't wish to ask here, you can email, because sir has already given the email to us. You can write to sir. Sir will reply to you. So, sir, what I will do, I will share your email ID. Already you have given, and our participants will write to you.
Sure.
Yes, sir.
Thank you.
1 minute, sir. I will propose a vote of thanks, and then we will conclude this session. So, Professor Dinesh Kabra, sir, has given a very excellent talk on emerging photonic materials and their applications in optoelectronic devices. Though due to short of time, we could not have the direct device level applications. Sir has covered a lot of basic things and synthesis related part, wherein you can at your own laboratory level, college level, with a simple setup, with a very cheap materials, you can start the research in photonic materials. I was listening, sir has given examples. Within 20 rupees, you can buy some chemicals. Means with such a small cheap things, you can start the research and you can develop, synthesize your own photonic materials and use them for the multi-junction solar cells or any other applications. Sir is always there to assist us. We even though we have even though if we have not answered the questions here, sir will assist you in all questions. Apart from this, you write him regarding the guidance in your research work. Sir will be there to guide us. Thank you, Dinesh sir, for your thought-provoking and excellent lecture. Thank you, sir.
Yes, and one more thing I want to basically mention here to
Yes.
the like young faculty members of your colleges and the students as well, that
Yes.
IIT Bombay and IIT Bangalore, both of them have got something called INUP,
Okay.
Instant Nano User Program,
Yes.
and we also have something called PUMP, Photovoltaic
Yes.
Mental User Program, where
Yes.
we basically accept the proposals coming from the young faculty members of those PSUs or some other small universities, colleges who
Yes.
want to pursue some kind of research project, and they just need to send the proposals, and we don't charge them anything. We basically facilitate all the research work. We pay them the travel, we pay them the accommodations, we pay them the consumables,
Yes, sir. Thank you, sir.
and that is all in order to ensure that upliftment of the our nation, because these are the students who are going to come and do the PhD with us.
Yes, sir. Yes, sir.
The young kids,
Thank you, sir. Sir, the name INUP.
INUP, IISc, INUP, IIT Bombay.
Yes, sir. IISc and IIT Bombay.
You find
Okay, sir.
there are websites, you can submit the proposals there, and those proposals are being accepted very quickly.
Yes, sir.
Okay.
Sir, once again, thank you. Dear participants, today we had a very excellent personality from who is a Cambridge fellow, who has worked at Cambridge University for a long time. He is working at IIT Bombay. He has worked with the Jawaharlal Nehru Center for Advanced Research. All the Institute of Immense he has worked, and we are fortunate enough to have such a excellent personality on the topic emerging photonic materials and their applications in optoelectronic devices. Thank you, sir. On the behalf of myself, on the behalf of my institute, शिव छत्रपति शिक्षण संस्था राजर्षि शाहू महाविद्यालय लातूर. I thank you all, sir. Thank you, sir.
Yeah, thank you.
Yes.